Okay, now we're on to problem number 6 in the 2019 B test. This question is actually one of the harder questions in the test. So, to begin this question, let's think about what it really means. It says if the dust is only held together by gravity, the density of dust is proportional to something. Let's first think about what does it really mean for the dust, for the very long cylinder of dust to be held only together by gravity if it's spinning at angular velocity omega. So we obviously know that if it's spinning around in a circle, it must have this force, right? mv squared over r, the centripetal force. It must have this force acting on it in order for it to be going around in that circle. If the dust is only held together by gravity, what that means is that the force of centripetal is the only force of gravity is the only force of centripetal force that's working to making this condition hold true. So that means that mg is equal to mv squared over r. So that means that if the dust is only held together by gravity, the gravitational field strength at all the radiuses should be equal to v squared over r, or equivalently omega squared over r, which is what we really should be using because they give us omega. So this is the condition that must hold true if it were to be held together only by gravity. Now we want to find what the density of the dust is proportional to. Where we can start is actually figuring out what is G. Find a equivalent equation for G that has density in the equation. So how we do that actually is something called the Gauss's law, but used for gravitation. I'm not sure if you guys have heard of it before, or heard of Gauss's law before, but once you learn electricity and magnetism, it's one of the fundamental Maxwell equations. But basically, Gauss's law for gravitation is if you take the closed integral of this dot product, then that's equal to negative 4 pi g times the mass enclosed. So you can see that this is really similar to, for those of you who know Gauss's law, it's very similar because you're looking at the gravitational field instead of the electric field and over a closed interval, and then you're looking at the mass enclosed instead of the charge enclosed by this closed integral, by this dA. So this will actually give us the equation for G, for the gravitational field strength. We're trying to find G right here, right? So we first let's look at this really long cylinder, okay? So at a certain radius r, let's draw. Say right here, certain radius r. So r can be anywhere within the cylinder, okay? If you actually, why don't we just call r up to here, just for simplicity's sake. If the gravitational field strength g, small g, at all points along this cylinder, the surface of the cylinder, they're all going to be the same, right? Just because of symmetry, because they're all symmetrically distributed in this along this axis right here, right? This is central axis. So it makes sense that given this cylinder, even if the density were not constant, the gravitational field strength will still be the same at all points in a certain radius away from the center. So this integral can actually be simplified. Instead of using an integral sign, we can just say g, right? Because the gravitational field strength does not depend on the area that it's going through. So we take it out of the integral, and then take the integral of this dA. And this is a lot easier. This is just This is just basically the area that we're looking at. The area that we want to enclose is going to be negative 4 pi g times mass enclosed. So let's say at a radius r, okay, that's the closed integral we're choosing for dA, okay? So that means that g, and what is the area of this closed integral? Well, it's going to be the area, okay, so be careful here because area is not volume. Actually, the area that we're enclosing is just 2 pi r times h, right? The h is the height of the cylinder. It's going to be really, really large. Okay, and then plus pi r squared, 2 pi r squared, okay? But we actually don't need to consider the plus pi r squared because in the question it says a very long cylinder of dust. So we're assuming that h is much, much larger than r, so pi r squared will have no effect in this equation right here. Let me just draw a little separation. So this is g, so this is the left side of the equation right here, g times 2 pi r times h. Okay, and then negative 4 pi, this is still the same, g times mass enclosed. So this is actually where it becomes useful for us. We can actually say the mass enclosed in terms of the density, because remember, we know that mass over volume is equal to density. So the mass enclosed divided by pi r squared h. So r in this case, if we just recap a little bit, r in this case is just at any radius that we choose to be from the center of the cylinder. So we can say the exact same r here, because that's the volume that it takes up, and that's equal to this density, okay? This density could depend on r, but we don't know yet, so we just write it like this for now. Okay, and then we will plug in mass enclosed to this equation right here. So multiply by pi r squared times h on here, this side, and plug it in. So then you get g times 2 pi r h is equal to negative 4 pi big G times pi r squared h times this density, which may or may not depend on r. We don't know. So we can simplify some terms here. We can get rid of this r squared term, get rid of this h term, and we can get rid of this pi here, and we can get rid of this, put this 2, so get g is equal to negative 2 pi big G times r times the density, which may or may not depend on r. Okay, so this is good. We found an equation for g that we can plug back into here for the condition that must hold if the cylinder was held together only by gravity. So if we plug this into here, we can actually get an equation for the density as a function of r. So let's plug that in. So we have negative 2 pi gr rho is equal to omega squared times r. So these r's cancel out. So we're left with the density, which depends on r, is equal to omega squared over negative 2 pi g. Now, this is actually going to give us our answer. And the reason is because omega is held constant, right? It says in the question, it's held in a steady state. So then, angular velocity omega at a steady state. So omega is not changing as a function of r. Okay, obviously these are all constants. So that means that the equation for density actually does not depend on r, right? So the answer to this question is that the density does not depend on r.